Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, Vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. So today we are going to start with a topic of prime importance in particularly the semesters examinations of engineering colleges. We have seen that we are often given to convert PFDs, that is process flow diagrams, to P&IDs, that is process and instrumentation diagram. Now PFD stands for, let me tell you, PFD stands for process flow diagrams. That is the basic flow diagram for a particular industrial process flow diagrams. And P&ID, as everyone should be aware of by now, stands for process and instrumentation diagram. So it basically, as the name suggests, instrumentation diagrams. So as the name suggests, you can see that this P&ID consists of certain instrumentation terms, that is the control elements has to be looked after whenever you are drawing a process and instrumentation diagram. Supposedly I am drawing an entire industrial process, but there is a need to have control elements on particular sections of an industrial process. Supposedly for a particular reactor unit you need to have certain control elements so that the pressure doesn't shoot up infinitely, or the temperature doesn't shoot up infinitely, or the level of a liquid doesn't rise infinitely. So you need to have certain control elements, and you need to create certain provisions so that those things like pressure, temperature can be controlled. You need to, supposedly the temperature of a reactor is shooting up, you need to keep some cooling arrangements to cool down the temperature. So these instruments that basically support the analyzation of any change in the system and try to control it through various instruments is basically entire process and instrumentation diagram. This is what P&ID deals with. So coming to straight away to two prolific examples which are very common in industry, that is a reactor and a distillation column. For a particular, particularly these two units, we are going to talk about how to draw the process instrumentation diagram from a basic process flow diagram. Like for a process flow diagram, we see that this is the feed to a distillation column, and certain amount of product is coming from the top as distillate, and certain amount of product is coming from bottom as the residue. So we can see that in a distillation column there has to be some control elements. Like if I talk of the reactor at first, let us talk about the reactor at first. You are seeing that reactants are entering the reactor from the top and are exiting the reactor from the bottom. Now this can be an horizontal arrangement as well. Now what are the control elements? What is the reactor control element? Firstly, the pressure has to be scrutinized. So to scrutinize the pressure, there are some basic rules or basic elements that you need to keep in mind whenever you are drawing this P&ID diagram. So firstly, there is this PE, that is, these are notations that you will have to remember. This is PE, or rather commonly known as PG, that is pressure gauge. This is the pressure measuring element. So this is pressure measurement. Similarly, TE also stands for temperature measuring element, that is the temperature element. So you now first need to measure the pressure. Now whatever you measure, this is the pneumatic signal, that is, it will be measured in kPa or something. It is to be measured in terms of mmHg, that is, it will be in pneumatic terms, and then you need to show it on the screen of a computer supposedly. So you need to convert those pneumatic signals into electrical signals so that they can be read, the pressure can be read. This is 100 kPa, this is 200 kPa, so you need to read the pressure. So first and foremost, there has to be a pressure element in the reactor. Supposedly I am drawing a pressure element. So the pressure element is represented in this sense, supposedly I am saying. So there is this pressure element that you need to measure the pressure through. Then this pneumatic signal basically gets converted into electrical signal. So it is dotted lines basically, but in the industry it is not very prolifically so. However, in detailed approach, you will see that these pneumatic signals do get converted to electrical signals. Now to detect the electrical signals, we need a transmitter. That is a pressure transmitter has to be there. So after this pressure element, there has to be a pressure transmitter which can read these electrical signals and can basically show it in digital format. So you need to understand, you need to analyze the analog signals, that is the pneumatic signals. You need to convert it into electrical signals so that they can be shown digitally. And finally there is going to be a pressure indicator or pressure indicator controller, that is PIC. If I write this like this, this is pressure indicator controller, and PT is basically my pressure transmitter. So you see, now this, if I write only PI, it would indicate that I am only indicating pressure, not trying to control the pressure or something like that. But whenever I am stating that it is PIC, I am trying to control the pressure. I am indicating it on the signal board and trying to control it. So basically, whenever there are certain changes in the reactor itself, you will see suddenly the pressure shoots up. So you need to measure the pressure, you need to convert it into electrical signals, and finally you need to control it. Now how will you control the reactor pressure? If the pressure reaches a certain height above which it cannot be withstanding or it cannot be further allowed, straight away this PIC will be directed to a valve. This is the relief valve, supposedly. This is the relief valve. That is, at emergency situations when the pressure shoots up too much beyond a certain level, this PIC will control the valve straight away and it will keep on releasing the excess amount of gaseous pressure that is being developed. So it is a release valve that opens at the call of the PIC. So this is basically my controlling element, controlling factor, this is, and this is my FCE, that is my final controlling element, FCE, or actuator, also known as the actuator. So basically, first to measure the pressure, then to transmit, and then to indicate and control it through a valve system. So you need to find ways to do this. Now coming to temperature, if the temperature of the reactor shoots up, so we need to keep this is pressure gauge PG, let me write this PG. So you basically would see that this is my temperature element, TE, it's being shown like this, branching coming out of the main stream trying to measure the temperature. So from the temperature element we would further move on. When we measure the temperature element, we would further move on to the TT, that is the temperature transmitter, which is hence converting this pneumatic signal or whatever the temperature element is measuring into electrical signals. And then we move on to TIC, that is temperature indicator controller. And how do we control the temperature? We keep a cooling arrangement, that is some cooling water or some cooling fluid, and we basically control the flow of the cooling fluid. So we control the flow of the cooling fluid through the jacket of the reactor. By controlling the flow of the cooling fluid, if the temperature shoots up, the cooling fluid flow is increased into the jacket. If the temperature falls down, then the cooling fluid is decreased, that is, it will not cool easily. But whenever the temperature shoots up too much, you need to bring in extra cooling fluid into the jacket. So this has to be controlled. So basically it is this temperature element, then followed by a temperature transmitter, then followed by a temperature indicator controller. If you only need to indicate and you do not need to control, then it's going to be replaced by TI and there will be no final control element. So basically this can also be a probable structure. You are measuring the temperature element, you are sending it to a temperature transmitter, and then you are just showing it through a temperature indicator. So it indicates the temperature and does nothing. Now, nothing else. Now, talking about let's rub this, talking about alarms. Now in this system only, we can have basically two alarms raised up from the TT itself, that is temperature transmitter itself. One is temperature high alarm, another is temperature low alarm. That is, we along with this automatically controlled final control element, we need to keep an alarm which provides us that if by some means this final control element fails or this temperature indicator controller fails to perform its function, there has to be something to detect a heavy rise in temperature. Supposedly I'm keeping a control element, but still we are seeing the temperature is shooting up too much beyond control, then this temperature high alarm will be there. Or if the temperature is falling too much below the expected rate, there will be a die-away of reaction. This will be a runaway reaction. A runaway reaction, if we do not control it, this will be a die-away reaction. So the reaction will not happen for an exothermic reaction or another where you need to supply it. So there are factors you need to keep in mind, that whenever this fails, there has to be some alarms in the system. So basically this TT is accompanied by a temperature high alarm and a temperature low alarm, which functions only when the temperature shoots up above a certain level due to misfunctioning of some of the things here. So you see, these are the basic elements that you need to keep in a P&ID. So PFD is much simpler. P&ID people complicate it because it's a big diagram with lots of control elements and measuring elements and transmitting elements, a lot of this and that. But basically it is nothing but the acquisition of the knowledge of what to control and how to control in a system or in a particular unit. So you need to just work it out for one particular unit, and then you can follow it throughout the line. Supposedly in a line you need to measure the pressure. You keep a pressure measuring element, you keep a transmitter after that PT. So you keep the PG, pressure gauge, after that you keep the transmitter, and then you keep the pressure indicator. It will indicate the pressure. And basically you keep a pressure high alarm and pressure low alarm here. So if the pressure shoots up, the operator will come to know about that pressure low alarm. So you see, this may seem as a very complicated diagram for a particular line if you have to do it, but it's actually the case done in an industry, followed in an industry, and this has to be drawn. It's not actually a complex thing if you understand the basic concept. Measuring element, transmitting element, and then indicating element or indicating controlling element, and high alarm and a low alarm associated with the transmitter itself. So coming to the distillation column now, I'm rubbing this one and I'm coming to the distillation column straight away. I'm rubbing the case of the reactor because primarily we are done with it. I'm rubbing the reactor. So coming to the distillation column. So a feed is coming at a certain temperature and a certain pressure into the system, and some distillate is going at the top, some bottoms is coming, as I've already mentioned. So what are the measuring parameters that you can measure here? You can probably measure the level. So there will be this, I'm drawing it here because it's going to be untidy otherwise on this side. So there is going to be a level element. By now you should be realizing that there should be a level element that should measure the level. Then there should be a level transmit. From there on there should be a level high alarm. If the level increases too much in the reflux drum, this is the reflux drum basically. So you are measuring the level there. It shouldn't increase too much, neither should it fall too much, so level low alarm. So you have to keep an eye on both. Now coming from the level transmitter to below and drawing a level indicator controller, LIC. Surprisingly it's LIC, but it's actually level indicator controller. So it indicates the level, that this is the level, and it controls the level. Now you need to have a controlling element that will control this level. Now you can see how to control the level. What are the basic things that comes to your mind? What is the input in the system? This input is from here. If you change the input, there are going to be a lot of factors that are going to be associated with it. You cannot change the input to this reflux drum. What you can change is the output to the reflux drum. You can send some output here, you can send some output here. Now, if by any means you see that the level is rising up, So basically, if your product line is fixed that I am going to produce this much of product every day and I will not produce excess of distillate. So if the reflux drum level rises, you will have to send it back into the reflux. Just reflux it back. Just reflux it back. So this LIC will basically have a control element associated with this line that controls the reflux. So there is going to be a valve here. If I just draw it a little bit enlarged the diagram, this is the first plate and this is my reflux line and this is my reflux drum supposedly, and the level is shooting up, and this is my level element, level transmitter converted to a level indicator controller. If I see LIC, this will basically have a control over this valve. So whenever the level shoots up, this valve will open up to allow extra liquid to flow in as reflux. So it increases the reflux. Whenever the level rises, the valve opens up to increase the reflux so that the level again falls down. If the level falls down, it decreases the reflux. If the level falls down, it decreases the reflux as well, so that the level can be brought back into the same position as it was. Now talking about the other parameters, if we come closely, observe closely, what are the other parameters? One can be the temperature here, the temperature element. So I'm measuring the temperature element maybe by a TE. Then I'm sending it to a TT. I'm attaching a temperature high alarm and a temperature low alarm, which I'm not showing. So it will be temperature high alarm, temperature low alarm. And finally, a temperature indicator controller. So it indicates the temperature as well as controls the temperature. How does it control the temperature? If the temperature is too high, it is supposedly a case of carryover of some liquid. That is basically some amount of liquid is being carried over by the vapor along with itself, causing flooding, the condition of flooding. If the temperature here is high, so what it means is some amount of liquid from the bottoms whose temperature is high is being carried over to the top, and hence the entire force is increasing the temperature. So flooding can be a cause of increased temperature. Temperature increasing, you will have to guess that this is flooding. So to avoid that thing, you can have a reflux here. There is the pump around reflux. But if you do not have a pump around reflux, supposedly, what you can do is you can basically increase this reflux as well. If you increase this reflux, that is, if this is my reflux drum and this is my reflux, and if my PIC is here, so the indicator controller says that the temperature is shooting up high, and if I keep the controlling element here, so it's basically opening up the reflux. So if the reflux increases, what happens is the liquid tries to pressurize it through the column to fall, to increase the flow of liquid, and the flooding is stopped. Flooding occurs basically when the vapor flow rate is much higher. Vapor flow rate is much higher than liquid flow rate. So if we increase the reflux, the liquid flow rate shoots up. The liquid flow rate shoots up. Liquid flow rate in the column shoots up if we increase the reflux. So if we increase the reflux by some means, the liquid flow rate will increase, and flooding, that is the liquid carryover, will be decreased. And once the liquid carryover is decreased, automatically the temperature will fall down. So TIC have a control over the reflux line. So these are the instincts that you will have to go with. There can be two pressure indicating elements here. Basically PG and PG combining to a PT, and then they are combining further to a differential pressure gauge. So basically it is giving the differential pressure between the two plates that are being considered. We are measuring it with the pressure gauge, the pressure transmitter, and finally the difference is being measured in a pressure DPGI, that is differential pressure gauge indicator. Now what do we see? If supposedly the temperature shoots up here, we measure it through a temperature element. If it shoots up here, so you need to control the temperature by increasing the reboiler duty or decreasing the reboiler duty. If the temperature falls down, you need to increase the reboiler duty so that the temperature can be controlled. These are the parameters that you need to measure and control in a particular system, and this is how it is to be done. There are several units in a particular industrial plant and you have to consider all of them. So I'm not discussing all the units in details, but I've made you understand probably what is the basic structure that you need to follow. So I think that's it for today, and if you liked our work, share it, like it, share it to your friends, comment on our work, and subscribe to our channel. Thank you.